Today we'll be talking about mass spectrometry, which is a technique that we use to tell us a lot about how a molecule can fall into different pieces that are kind of like a fingerprint for the molecule. In mass spec or mass spectrometry, we always start out with a sample that gets vaporized immediately. So we're really dealing with things initially in the gas phase. That gas phase molecule doesn't give us much information about the mass, but we can get more information about the mass if we ionize it. So we use something like a beam of fast-moving electrons in order to actually strip electrons off. When we do that, we end up with radicals that are really unstable and will start to fall apart in predictable ways. Again, we'll end up with a positive charge. The positive charge is easy for us to detect, and if we can differentiate based on mass, that gives us a lot of information about the molecule. The process that we have for ionizing in our instruments is called electron impact ionization. We take an electron beam and we make ions. This is considered a hard ionization. It breaks things into lots of pieces. There are soft ionization techniques that are able to break into fewer pieces, which are really useful for looking at big molecules like proteins in biology. Mass spectrometry is going to be set up so that we have a sample source that gets vaporized right away, and we create the charged particles in between two charged plates. So we use an electron beam, which we can see kind of right here. That electron beam will create ions, and since those ions are in front of a positively charged plate and behind a negatively charged plate, they will quickly accelerate in this direction. Some of those will hit the accelerating plate, and that's fine. We're not looking for a quantitative conversion. We just want to see all of the types of things that are being formed in relatively normal ratios. Since we have lots of individual molecules in a sample, we tend to have plenty of signal to give us good statistical data, even if a lot hit the sides. As they accelerate this way, we can turn them at different rates depending on their mass by a magnet. Smaller particles are going to be more susceptible to change. The least massive ions are going to be deflected the most. They're going to change their angle over more this way. And the most massive samples are going to change the least, and so they'll stay more straightforward. This allows us to differentiate those different masses, which can be a really helpful thing. A charged species, again, can be guided to different points on the detector, and the detector is sensitive at different points, so it can tell what charge is, or how much deflection has happened for a species. And if it's calibrated, that correlates to a mass to charge ratio, M to Z ratio. Z is the same type of Z that you see in some of your Gen Chem proton or nuclear charge calculations. Typically, our mass to charge ratios are based on charges of 1 because it's a lot more likely that you're going to ionize just once rather than multiple times. These detectors will keep track not only of what hits, but also how many times it gets collisions. And so it will tell us what types of things are most commonly formed and what types of things are least commonly formed, the relative abundance. We have any given molecule will fragment, that means fall into pieces, in really predictable ways. And so, for example, we have a hexane right here. The hexane will have a mass plus peak. That mass plus peak corresponds to the weight of the entire ion. We can calculate that based on, we have carbon 6. That's going to be 6 times 12, or 72 mass units. And we're going to have hydrogen 14 on hexane, so plus 14 gives us the 86 that we see right here. And that's usually the highest big peak that we see, that mass plus peak, but we also see a couple of other really important peaks on this spectrum. We will also see a peak that is at greater intensity. We call that the base peak. The base peak is the peak that has the most abundance. We set that abundance to 100%, and then we have everything else relative to that highest peak. So here our base peak is 57. That's our most stable ion that can be formed. And our mass peak is less stable, so we see less abundance of that ion. On this, we also see a mass plus 1 peak. That's this real tiny peak right here. That's because we don't always have the exact same isotope of a molecule anytime we're looking at mass spec. And so if we happen to have a carbon-13 somewhere in the molecule or a deuterium, we would end up with a slightly more massive. When we form a positively charged radical ion, those electrons are usually stripped off from the highest energy orbitals, which in this case are actually the sigma bonding orbitals between any carbons. Depending on which carbon we are ejecting an electron from, we end up with a number of different possible fragments that can be formed. So if we eject an electron from this site, we can end up splitting that into a carbocation that is not a radical but just still has a positive charge, and an uncharged radical. The dots for the radical aren't written here, but this one is uncharged because it has a single electron. This is what we actually detect. We can't actually detect the radical, and it actually matters a lot more for charge stability. Notice that in this case, we have an electron deficient piece with a positive charge on this carbon. That's a primary carbocation, which is not particularly stable. And we have a methyl radical, which is also not particularly stable. In this second one, where we split between the fourth and fifth carbons, in the order that's drawn, we have a positive charge on the rightmost carbon here, and we have a radical here. Now we have still a primary carbocation, but we have a secondary radical, which is a little bit more stable. And if you remember from the last slide, this is actually our base peak. This is the 100% abundance peak. So this is the thing that is most stable, because moving up to have a primary radical improves the stability so much. This is not that much less stable to have a primary and carbocation and a primary radical with equal size pieces, just a slightly less stable molecule overall. In addition to fragmentation, which we'll actually talk a lot more about in the inner chapter, the next set of slides, we can get some important information from the mass plus 1 peak, which has to do with carbon-13 isomers mostly, and the mass plus 2 peaks, which have to do with halogen isomers mostly. Because we know that the isotopes, the N plus 1 peaks, are coming from carbon-13 in most cases, we know that we're going to have a much larger chance of having a carbon-13 in the molecule if it's a longer molecule, because it doesn't matter which carbon swaps out for carbon-13, they'll all give the same mass plus 1 peak. We'll have more versions of the molecule that can give mass plus 1 if we have more carbons that can be carbon-13. We can actually use this to estimate how many carbons there are in a molecule, which can be pretty helpful statistically. So we might say that the number of carbons is going to be about equal to, so we'd say, maybe plus or minus 1, or at least rounding up and rounding down to consider which is better fit. And we'd say it's going to be about equal to the intensity of the mass plus 1 peak relative to the intensity of the mass plus peak. So we just measure the heights and see how those are different, or see what the percent abundance is. And we know that we should have an abundance of 1.1% over 100 if we just have one carbon. So we multiply by 100% over 1.1, and that tells us how many carbons are likely to be found in that molecule. We can also give a lot of information if we see mass plus 2 peaks, because mass plus 2 peaks often come from halogens. Chlorine, because it has both 35 isotope, which is more common, and a 37 isotope, which is 2 higher and about a third as common, we'll always see the mass plus 2 peak at about a 1/3 ratio of the mass plus peak. Those isotopes are both fairly common, and so we can use that to tell us a lot about the molecule, and even fragments that have chlorine on them as well. Bromine also has a similar known ratio, so we have bromine tends to be 1-to-1 ratio. We have bromine 79 is our mass plus peak, and bromine 81 is our mass plus 2 peak. And so if we see a mass plus peak and a mass plus 2 peak that are very similar, we have a good indication that there's bromine in the molecule. There are lots of molecules that have naturally occurring isotopes that are fairly common. So the ones that are going to give us the clearest information are the ones that are highlighted in red here, because they have a relatively significant abundance. So we saw that carbon-13 could tell us about how many carbons are in the molecules. There shouldn't be a big surprise that pretty much every one of our molecules is going to have carbon in it in this class. Halogens are, particularly chlorine and bromine, are also really helpful because they have 25% abundance of the less common ion for chlorine and almost 50% abundance for bromine. You can get some information from the mass plus 2 peak for sulfur. You'd have like a 1 to 25 ratio, so it's not as helpful as it might be if we had a more abundant ion, but that can still be pretty useful. And for silicon, we can also get pretty decent peaks. Notice now we'd have one major peak that would be about maybe, well, whatever, 92.23 divided by about 4%, maybe about 30 times as high as this one, and maybe about 18 times as high as this one. We can see these mass plus 2 peaks for the molecule itself, and that's relatively straightforward. We can find the mass plus peak by looking for the largest cluster of ions, and if we have one that's at 2 higher than another one that's about the same ratio, that gives us a really good indication that we have a halogen. And if they're, again, equal, we'd say that this is probably going to have bromine in it. And we see the mass and mass plus 2 are only 2 apart, and they have about equal heights. Notice that there's other groupings around here. The spectrum's not clean. There are lots of different things that can happen in really small amounts to a molecule, but we're looking for the major peaks in each region. Notice we actually also have another peak over here. It's fairly common for us to be able to strip off halogen and leave behind the other radical, particularly if it's an aromatic radical. And so our base peak actually comes from the aromatic itself. Notice that we have 6 carbons, so 6 times 12 would be 72, and we have 5 hydrogens on here, so we'd say 72 plus 5 equals 77, and our base peak is just this aromatic without the bromine and having a single electron, or sorry, having a positive charge there. Notice that we still have that same peak down here, but it's we also have an added isopropyl group, so that's our base peak if we have the 77 plus all the mass from the isopropyl group. But we can also tell a little bit about the molecule if we look at certain fragments that are higher up in this molecule. So of course we have the mass plus peak and the mass plus 2 peak up here. Those indicate that there's a bromine in the molecule. But we also can see that there's a fragment that contains bromine because there's another set of peaks that are 2 apart of about equal height, and we know that those contain bromine. There's even a not particularly stable fragment down here that also contains bromine. So looking for these 1-to-1 ratio mass and mass plus 2 peaks, or having a 3-to-1 ratio in a mass plus 2 peak can be really helpful for identifying what types of molecules we have. In addition to giving us some information about the presence of chlorines or bromines, we can also, as we indicated before, use this to tell us a little bit about how many carbons we have. So if we use this as an example, we know that we have 2.4% abundance for our mass plus 1 peak, and we have our mass plus peak is 30.0. We don't need to include the percents, we just need to have them in the same unit in both cases. So 2.4 or 0.024 are both fine as long as we match it up with the correct form down here. Anyway, if we actually calculate this out, we'd say that we have 7.27 carbons. Notice this is an about, it's not an exact, and so we'd say, yeah, there's probably either 7 or 8 carbons in this molecule. From there, we can say, well, what would we expect if this was all carbons and hydrogens, like if it was a saturated molecule? If we had C7, we'd expect to have H16 for our overall formula if it was saturated, and that would give us 7 times 12 is 84, plus 16 is 100. So obviously that's too low. There's got to be something else in the molecule. So maybe we'd have something like C8H18. If we did that, we'd have another 14 mass units, 12 from the carbon and 2 from the additional hydrogens, and so we'd say that we have 114. That's still not actually enough to get to this mass plus peak, which is 129. We could try to put in another carbon, like another CH2 group, we are saying that it's about, and this is dealing with statistical data. But if we added another 14, we'd be at 128, and there'd be no way of getting that odd number here, the 129. We typically only get odd numbers, at least in any sort of common ions that don't have halogens, through nitrogens, right? Because when a nitrogen is added to a molecule, say like if we have a propane, that would have C3H8. It has a mass of 36 plus 8 is 44. If we put a nitrogen instead of the carbon, we'd have C2H6 from the carbon, but we have the N always comes with the H as well, because it can have 3 bonds instead of 4. And so even though nitrogen has an atomic mass of 14, it always comes in units of 15 because it brings along an extra hydrogen. That's a way that we can actually get us to the right amounts of mass if we have an odd number. Odd number masses tend to indicate nitrogens. So if we have 114 and then we add an NH group which weighs 15, then we end up with 129, which is actually what we want.